The purpose of this video is to learn how to handle variables on the right side of our regression equation, whether linear regression or logistic regression, that are categorical. So we have already talked about continuous and categorical variables on the left side of the equation, the outcome side. We've talked about continuous variables on the right side of the equation, but we haven't yet talked about how to handle categorical variables on the right side of the equation. So far, we've just used a shorthand version to say that we would have a categorical variable and we decided how many levels that we were going to use. But what we need to do is we need to transform these categorical variables into a form that we can actually use in our regression models. So that's the step we're going to take in this video. So we already looked at continuous variables on the right side of our equation. We said that the line that is represented by the structural part of our model tells us where the random number generator, here we have a continuous outcome. So this is generating a random number from a normal distribution with a mean of 0. And the structural part of the model tells us where the random number generator is located for any particular value of x, the variable in our model. And from there, the random component of the model is generated. And we looked at a picture of what it looks like when we have, instead of having a continuous variable on the right side of our model, we have a categorical one. So for example, here we were looking at the age at death, and we were looking at the association between that outcome variable, a continuous outcome variable, and the binary categorical variable smoker. And we can see here that the age at death on average is lower for smokers compared to non-smokers. So before we saw the mathematical structure of the model, but we haven't seen that yet for this kind of situation. So how would we structure this model? Well, we would have the age at death as the outcome, and it would be equal to some constant, beta 0, plus another constant, beta 1, times some variable to represent the smoker. And then we would also have a random component. Now the problem here, though, is that the variable smoker is not a number. It's a category. It's no or yes. So how are we going to multiply a category times beta 1? It doesn't make any sense. So one of the first things we have to do is we have to replace these names within the categories with numbers. And it's going to look like this. What we do is we change the no to a 0, and we change the yes to a 1. So for each individual, we will have a variable called smoker that we will code it as 0 and 1. 0 if they are not a smoker, 1 if they are a smoker. So if we have this kind of situation, what would be the values of beta 0 and beta 1? Well, one thing to notice is that when smoker is equal to 0, then this whole portion of the model will become equal to 0, because if you multiply any number by 0, the whole product equals 0. And when this value is equal to, smoker is equal to 1, then this whole product is equal to the value of beta 1, because if you multiply any number by 1, it's just the same number. So you can think of smoker here as a kind of light switch, on off. And so what will happen is when a person is not a smoker, this portion of the model, this beta 1, will essentially be turned off. And when someone is a smoker, then this whole portion will be equal to the value of beta 1. So it's simply we're using the variable smoker to turn this beta 1 on and off in the model. Now beta 0 doesn't have any multiplier, and so this is always going to be in the model. So what would be the values of beta 0 and beta 1 that would give us the right location of the random number generator? Well, when the value of smoker is equal to 0, We want the structural portion of the model to equal 85. When this is 0, this whole portion goes away. And so the only thing left for the structural portion of the model is the beta 0. Well, if when this equals 0, we want the whole thing here to equal 85, then the value of beta naught that we should use here is 85. And then what we want is when smoker equals 1, then this beta value is going to get added to this beta 0 value of 85, and it should give us the correct value for this group, which is 70. This is the structural portion of the model where we want the random number generator to be located. And so 85 plus what number equals 70? Well, 85 plus a negative 15 equals 70. And we have the, let me get rid of these arrows here for now because they're in the way. And we have still the, oops, this is not a plus, that's a times, the smoker and the random component. So this model, age at death equals 85 minus 15 times smoker plus the random component will give us exactly this. When smoker equals 0, this drops away. So beta naught equals 85. So then the age at death equals 85 plus the random component. And you can see that is correct for this group. When the people are smokers, for all the people who are smokers, this variable is equal to 1. And so then the placement of the random number generator becomes 85 minus 15, which is equal to 70. So then for all of the smokers, the age at death is given by 70 plus some random component, which is exactly this. So what we can see here is that this function gives us this structure. Now, one thing to notice here is that we had two levels of smoker, 0, 1, no, yes, and that was able to be codified in our model using one variable. So if you have two levels, you can code things with one variable. And the reason is because the group for whom the value of the variable is 0, their mean value, which is where the random number generator is going to be located, will be placed by the constant beta 0 in the model. And so that is taking care of the location for those who have one level of our categorical variable. And so we only need one more variable to take care of the second category. So two categories, we need one variable. What we're going to find out is that you always need one fewer variables than the number of categories you have. So for example, if I had a categorical variable here with 3 levels, I would need 2 variables in the model in order to code the structure of the model for those 3 levels. So 2 levels, 1 variable, 3 levels, 2 variables, 4 levels, 3 variables, 5 levels, 4 variables, etc. So let's look at an example of one. What if instead we were looking at the number of years that someone smoked in their lifetime, the smoking duration. And we had 3 categories. They never smoked, they smoked less than 10 years, or they smoked 10 or more years. And say these were the data that we observed in our population. Now, how would we code this? Now, if we have a categorical variable with 3 levels, the way that we have done it so far is that we have started the bottom group at 0 and then gone up for each category. So this in your data set, if you have this variable, it would be smoking duration with 3 levels, and you would have coded it 0, 1, and 2 because that's the way we said. Now, can we set up a model that just has the age at death equals beta naught plus smoking duration plus a random component? This kind of model is possible to set up. It would be a kind of model of a linear association between smoking duration and the age at death. But what we can see here is that the relationship is actually not linear. It looks like, for less than 10 years of smoking, the decrease in the average age at death is about 5 years. But for greater than or equal to 10 years, the drop in the average age at death is about 15 years. So the drop in the average age at death for each step is not the same. So this is a nonlinear relationship. So the relationship would look something like this. So for this kind of nonlinear relationship, we don't want to force a linear relationship, because what's going to happen is that the model will come out something like this. Probably something like that, which is a little bit off from what we see. So we don't want to set up our model in this way. We want to give it the flexibility to allow the difference between the categories to be a nonlinear relationship. Essentially, if we set it up like this, we're treating a categorical variable like a continuous variable. It's just going to be basically the change in the continuous variable. It's just going to be essentially the beta 1 is going to give us a slope here. But remember, these numbers don't actually represent things that we have measured in some scale. These are categories, and we're just using these numbers as a kind of mathematical shorthand for the different categories. These are just category markers. And if we want to set up a mathematical function that works with the categories, we need to use what are called dummy variables. And that's what we actually did in the previous example. We used one dummy variable to create the structure of a model for a categorical variable that had 2 levels. And one of the things about a dummy variable is that a dummy variable will always be coded 0 or 1. Now, what we have over here is we have a variable that has a 0, 1, and a 2. And another thing about a dummy variable is that a dummy variable will always have exactly 2 categories, 0 and 1. And here we have a variable with 3 categories. So for a variable with 3 categories, we said that we would need 2 variables in our model to structure our model to be able to handle the 3 categories in the structural part of the model. So let's learn how to create these 2 variables for a 3-level categorical variable. And what we're creating here are 2 dummy variables to put into our model to structure the model to be able to handle what we see here without imposing a linear relationship between the categories. So let's say this was our variable. It's smoking duration, and so it's smk_dur. It has 3 levels, so I put a 3 here. And it's coded 0, 1, or 2. Zeros are never smokers, 1s are people who smoke less than 10 years, and 2s are people who smoke 10 or more years. So if we're going to create dummy variables for this, we have 3 categories, and so we're going to need 2 dummy variables. So the way I like to code, or rather name dummy variables, is I keep the same name for the first part of the variable name, but then I add an underscore, and then I add a number to indicate a particular level in the original variable. And we're going to forget the 0 level. We're going to use the 1 and 2 level. So I'm going to create a dummy variable for the 1 level, and I'm going to create a dummy variable for the 2 level. And so the way this is going to be coded, when smoking duration 3 equals 1, then this dummy variable for that level is going to equal 1. Otherwise, it's going to be equal to 0. And so what's going to happen is the beta value that is associated with this variable is going to get turned on whenever somebody is in the group that smoked fewer than 10 years. And so for this level, this dummy variable for this level is going to equal 1 here, but it's going to equal 0 otherwise. And so what's going to happen is that this beta value is going to get turned on whenever the smoked years equals greater than or equal to 10 years. Otherwise, it's going to get turned off. Now, what about this group up here? This group here, who are the never smokers, for this group, both of these beta values are going to get turned off. And so how are we going to determine the level of the average age at death for this group if both of these dummy variables or the beta coefficients related to these dummy variables are turned off? Well, it's going to be the constant in the model. Remember, we only need 2 dummy variables to mark a 3-level categorical variable because we have the constant in the model. So let's write it out here. So the model here is going to be the age at death equals some constant plus another constant times our first dummy variable plus a third constant times our second dummy variable plus an error. So let's go back to our diagram and see if we can figure out what these beta values would be equal to by looking at the diagram. Well, the first thing I want to do here is I want us to remember the relationship between the original variable and our dummy variable. So let's write a little diagram here. So this is the smoking duration 3, and it's equal to 0, 1, or 2. And then we have two dummy variables. One is the smoking duration 3 underscore 1, and a second one is smoking duration 3 underscore 2. And for never smokers, both of these variables are equal to 0. For people who smoked less than 10 years, this one is equal to 1, but this one is equal to 0. And for those 10 years and greater, this one is equal to 0, and this is equal to 1. So let's think about this beta naught. We'll be able to see the value of beta naught here in the never smoking group because the two beta values, beta 1 and beta 2, are essentially going to be turned off by the zeros that will be for both of these dummy variables in the never smoking group. So the beta 0 here is just going to be equal to the placement of the random number generator in the never smoking group. So this is going to be an 85. So we can see that directly from our diagram. So this will be an 85. Now, in the people who smoked less than 10 years, the random number generator is located at 80. This is 5 less than for this group. Well, which beta value is going to convert this 85 into an 80? Well, it's going to be the first one here because this beta value, beta 1, is going to be turned on when the smoking duration is equal to less than 10 years, this group. And so this number plus the beta 1, which gets switched on for those who are under 10 years, this needs to equal 80. So 85 plus what number equals 80? Well, negative 5. So this beta 1 value is going to be a negative 5. And then what about this beta 2 value? Well, this one is going to give us the placement of the random number generator in the group that smoked 10 or more years. And so what's going to happen for this group is that this first dummy variable is going to be equal to 0. So this beta 1 value, this minus 5, is going to get switched off because it'll be times 0. So the only thing remaining will be this 85. So 85 plus this beta 2 has to give us the value here. So 85 plus beta 2 equals going to equal to 70. Well, what should the beta 2 value be? Well, 85 plus what number gives 70? Well, it's negative 15. So this is going to be negative 15, minus 15. So if you calculate using these dummy variables for each of the three groups, what you're going to find out in the first group, these two numbers are 0, so these two beta values drop off. So the number that we're going to get out of this function is 85, which is the correct value. For the second group, this one becomes a 1, so this is a 1, so times that. So this number comes in. So the value we're going to get from here is 85 minus 5 equals 80. That's the correct number. And then for the third group, this one is going to be equal to 0. This one's going to be equal to 1. So this beta value will be turned off. This is 0. This one will be turned on because this is 1. So 85 minus 15 is going to give us the value for this group, which is correct. And then all of them have the random component at the end. So here you can see how two dummy variables is sufficient to code the location of the random number generator for a categorical variable that has 3 levels. And it's always that you always need one less dummy variable than the total number of categories in each categorical variable. Okay, so here we are in SAS. This is the Create Working Data SAS program. And the first thing I'm going to do is I'm going to give it a new version name. So this will be version 4 for me. And so what I want to do is I want to go to all of my categorical variables and I want to create dummy variables for them. Now I know how many levels are in each categorical variable because I put the number at the end of the variable name. And so what I'm going to do is I'm just going to I'm going to create my dummy variables. When I recode the variables in the number of levels. So here I recoded things into 5 levels for race. I'm going to create my 4 dummy variables for race here. So the first thing that I would like to know probably is I want to just make sure that I'm clear about the levels, that the way the levels are coded in my variable. So I'm just going to do a proc frequency here. And I need to run all of my data first. So let me do that. Everything looks fine there. So now I can come down here and I can create the race 5 variable, and let's just see what it is. So it's coded 0 to 4. There are 5 levels, which is what it should have been from before. So what I want to do is I want to say if race 5 is equal to 0, then. Now I'm going to be doing more than one thing after the then statement. So I'm going to show you some new code here. If in an if-then statement, after the then, you want to do more than one thing, you can use this kind of syntax. You say do. If race 5 equals 0, then do. Then you can put a number of different things in here that you wanted to do, and then you finish it with end. So what'll happen is if race 5 equals 0, then it's going to do all the things you list between the do and the end statement. So for example, if I want to create 4 dummy variables, there would be race 5 underscore 1. And since this is the 0 level of the variable, all of my dummy variables are going to be equal to 0, like we saw before. In the previous example, when the smoking duration was equal to none, the level was 0, then our 2 dummy variables, the dummy variable for level 1 and the dummy variable for level 2, both of those dummy variables had a value of 0. So here we're going to create 4 dummy variables because we have 5 categories of race. When race 5 is equal to 0, then all 4 of those dummy variables are going to be equal to 0. So we're going to create a dummy variable for level 1, level 2, level 3, and level 4. And then we have the end statement. So there is a semicolon after each statement, after each definition of the value of the variable. And we have the do here and the end here. So if race 5 equals 0, then all 4 of these things are going to get done. Now, there are 5 levels of race, so I basically need 5 of these. 1, 2, 3, 4, 5. This one is going to be for 1. This is going to be for 2. This will be for 3. And this will be for 4. So when race 5 equals 1, then we want to have the dummy variable for level 1 equal to 1. Everything else 0. When race 5 equals 2, then we want to have the dummy variable for level 2 equal to 1. Everything else is 0, and etc. So level 3, we're going to turn this one on. Level 4, we're going to turn this one on. So this is how we create the 4 dummy variables for the 5 levels of race. And so what you're always going to have is, you're going to have the first row is going to be zeros, and then you're going to have the ones going in a diagonal like this. This is where the structure is always going to look. Now let's see if we did things right here. Let's do a proc frequency with a slash list and put our original variable against all of our 4 dummy variables. So it's going to be race 5 underscore 1 times race 5 underscore 2. So let's do this and see how it looks, just to make sure we coded things correctly. So here we can see when race 5 equals 0, all of these equal 0. When race 5 equals 1, this one gets turned on. Here for level 2, number 2 gets turned on, 3 gets turned on, 4 gets turned on. And here you can actually see the reason why I like to start coding variables from 0. It's because the dummy variables then become 1, 2, 3, and 4. So these 4 variables are the variables that are actually going to go into our model. Each one will have its own beta value, and the value for the 0 level is going to be contained in the intercept. Okay, we'll see more about that later on. So what I'm going to do here is I'm just going to comment these things out so that you can see them. Okay, so that's for race. Now let's do it for the sex variable. The sex variable actually is already a dummy variable, but just so that it has the same structure as the other dummy variables in our model, I'm going to just go ahead and write one. So this is going to be basically if sex2 equals 0, then our dummy variable is going to be sex2 underscore 1 is going to be equal to 0. And if sex2 equals 1, then our dummy variable is going to equal 1. So we have two levels of sex2 here, 0 and 1. We only need one dummy variable because two levels needs 2 minus 1 dummy variables. That's 1. And if the value of sex2 is equal to 1, then we want to turn the dummy variable on for level 1, otherwise it's turned off. So this is going to be our dummy variable for here. And if we come down here for education, we have 4 dummy variables here. So here, education has 4 levels, 0, 1, 2, and 3. So we're going to create 3 dummy variables. So let's create the first one. If education 4 is equal to 0, then do semicolon. And I'm going to create my 3 dummy variables. 1 underscore 1 is going to be equal to 0 here in the first row. 2 equals 0. educ4 underscore 3 equals 0. And then we have the end. And then I need 4 of these. 1, 2, 3, 4. This one is going to be a 1. This one is going to be a 2. This one's going to be a 3. Then we have this goes to a 1. This goes to a 1. And this goes to a 1. Now let's check it, make sure it's right. Proc frequency tables educ4, then 4 underscore 1, educ4 underscore 2, educ4 underscore 3 slash list, and then run. Okay, let's see how it goes here. Okay, so we can see that it came out correct. The 0 level has zeros all the way across, and the 1s are going diagonally. So we're okay here. Again, I will comment this out. So I've done sex, race, education. What else is here? Income. Was income? Yes, income was a 3-level variable, 0, 1, and 2. So let's go ahead and do this here. If income 3 equals 0, then do income 3 underscore 1 equals 0, income underscore 3 underscore 2 equals 0, and then the end, I have 3 levels, so I need 3 lines. This is going to be equal to 1, this is equal to 2, this is equal to 1, and this is equal to 1. Let's check it. Proc frequency tables income 3 by income 3 underscore 1 by income 3 underscore 2 slash list, and a run. Oops, that's not run. Okay, let's do this. Okay, something is wrong here. So I have some problem. This is why it's always important to check things. What did I do wrong here? If income 3 equals, did I not run this? Is that why? Oh, I guess I didn't run this section, did I? Is that what happened? Let me try this again. Yeah, that's what it was. I didn't run the section. Okay, so income 0, 1, 2. These are zeros. The ones are in the right place. So income is okay. So again, I'm going to get rid of this stuff here. And then years of smoking is continuous, age is continuous. So that's it. COPD is a binary variable, but it's not on the right side of the equation. So we're not going to do anything with that. These dummy variables are only for the right side of the equation. So I think I've done all of them. Let's see, I did sex, I did race, I did education, I did income, and everything else is either continuous or it's an outcome. So this is all that I need to do. So let me save this. Let me clear my log file. And let's run the whole program, see if it runs. Okay. So my lab names are okay. It's reading in everything all right. It's merging data okay. We've already checked all the dummy variables. And so it looks like everything is okay. All right, so that is it. So I have written a new working data to the hard drive. This is actually going to be the working data that we are going to pick up to start the actual analysis process. Okay, now that we've got all of the variables created for our model, let's look at what the actual model will look like. So let's first look at my linear regression model. My outcome is a continuous FV1 to FVC ratio. And so the structure of the model is going to be, we're going to start out with a constant beta 0. And then the first variable is the continuous years of smoking. And this will be one term in our model. So it's going to be plus beta 1 times the years of smoking. Age is also continuous. So again, it will be one term in the model. So it'll be plus beta 2 times age. Now, income is a categorical variable with 3 levels. So we will have 2 dummy variables, each with its own beta coefficient. So that will be plus beta 3 times income 3 underscore 1, plus beta 4 times income 3 underscore 2. Now the next is sex. It's a categorical variable with 2 levels. There will be 1 dummy variable. So plus beta 5 times sex 2 underscore 1. The next is race. It's categorical with 5 levels. So there will be 4 dummy variables. So plus beta 6 times race 5 underscore 1, plus beta 7 times race 5 underscore 2, plus beta 8 times race 5 underscore 3, plus beta 9 times race 5 underscore 4. Finally, we have education. It's categorical with 4 levels. So there will be 3 dummy variables. That will be plus beta 10 times education 4 underscore 1, plus beta 11 times education 4 underscore 2, plus beta 12 times education 4 underscore 3. And then we will have the random component, which is the error in the model. We can think of it as the number that's generated by a random number generator with mean 0 and a normal distribution. So the structural part of the model will be all of the parts that have betas in it, and then there is the one random component to the model, which is the epsilon at the end, and the structural plus the random together gives us the actual value observed of the FEV1 to FVC ratio. And for my logistic regression model, the odds of chronic obstructive pulmonary disease is going to be given by e raised to the power of the structural portion of the model. So the variables are exactly the same. The structural portion of the model is exactly the same, but how it's used in the equation is different than in the linear regression model. We saw this before when we looked more closely at the different model structures. So now I just want to think about, what does this beta 0 represent in a model where we have so many variables? We saw before when we had one categorical variable that this beta 0 was the location of the random number generator for somebody, for example, in the lowest level of income when we were looking at income. But what if we have all of these variables in here? Well, for the categorical variables, it's easy to think about. Well, beta 0 is essentially going to be the location of the random number generator when all of the variables in the model are equal to 0, because that is going to turn off all of these beta values except for the beta 0. So for the categorical variables, these beta 3, 4, all the way through 12, these are all the variables next to them are going to be equal to 0 when a person is in the lowest category of all of these different categorical variables. So that's pretty easy to think about. Now, for years of smoking, this beta 1 will be equal to 0 when the years of smoking is equal to 0. We have people in the
data set who didn't smoke at all, so their value will be 0. They'll have 0 years of smoking. But what about this age variable? Let's think about this one, because for my data set, I am limiting it to people who are age 20 and older. So there are actually no people in my data set who have age 0. So how is this beta 2 going to be set equal to 0? So for age, the way we think about it is that here we have the age, and we are, say, looking at individuals from 20 to, I forget what the upper end is. Let's say it's 80 years. I don't think it's quite that. It's like 76 years or something. And if this was the FEV1 to FVC ratio, we know that the FEV1 to FVC ratio is going to be decreasing with age. So how can we think about this beta 0 estimate, the location of the random number generator, when all of the values of these variables equal 0? Well, what the model is going to do, even though the model only has data in this range between 20 and 80, what it's going to do is it's going to, because this is a straight line, it's just going to extrapolate out to age 0. And it's going to consider what if this line continued over here, what would be the value of the FEV1 to FVC ratio at age 0? Now, this is not something that's going to be the reality. In reality, the FEV1 to FVC ratio increases as you're growing, and then it starts going down at age 20. So this isn't actually an empirical kind of thing. But for this period, for this range of data values in here, which is where we are looking at the data between age 20 and 80. This is a straight line. And so this beta 0 estimate, we can't really interpret it literally in the same way that we were doing before. It's more what it is, it's just a value that in the range where we are looking at the data, it will allow us through a function, through a straight line that is multiplied by the age in the range of values that we have, that will locate the random number generator at the correct place. And so the beta 0 is in fact the value of the location of the random number generator on the FEV1 to FVC axis when all of these variables equal 0. But because of this one, we can't actually say that this is the mean value of the FEV1 to FVC ratio for any actual group in our data set. Now, if this isn't clear to you, don't worry about it. This is really not necessary for understanding the model. I'm just including this for those of you who are perhaps a little more mathematical so that you can have a deeper intuition about what the beta 0 is doing. Now, what we're going to be interested in is we're going to be interested in the beta 1 value because this is the parameter for our exposure variable. All of these other variables in the model are just there to condition so that we can control for confounding. And what's important for us is that we will be able to interpret this beta 1 correctly and interpret that one correctly. We're not really worried about the beta 0. It's more a nuisance parameter in our model. So I think this is as far as we need to go with this. This is the structure of the model that we're going to use for the linear regression. This is the structure of the model that we're going to use for the logistic regression. And now, as long as we are coding our variables correctly in our data set, then we are ready to go to the next step, which is the modeling process. So what you want to do is you want to get your categorical variables converted into dummy variables so that you will be able to take that next step.